So do you ever think about the roles that machinery plays in your daily life? All the time? Well, most of us think about energy and how energy impacts our quality of life. And this chart shows the flow of energy throughout our economy. So starting on the left from different sources of energy, a lot of it goes up to the orange circle where it's converted to electricity, and then all the way to the end use on the right. And machinery systems are pervasive throughout this system. Starting in the lower left, you'll see oil and natural gas. Now, those two sources alone make up 3/4 of our energy supply. And so let's start with the machinery. Most of us are familiar with oil pumps. Oil pumps like that are used on small wells. Larger wells might use an electric submersible pump. And then as wells get older, we add more machinery to increase their production. We'll add a gas compressor, which is used for gas lift or enhanced oil recovery. Natural gas wells are similar. We use reciprocating compressors at each wellhead. We boost production through hydraulic fracturing, which uses a frac pump, another machine. Moving away from oil and gas, there's a lot of other energy sources that mostly all also use machinery. Geothermal systems use the Earth's heat, and they convert that to electricity through a steam turbine or an organic Rankine cycle turbine. Wind uses machinery. Hydropower uses machinery. Nuclear and solar heat use steam turbines, large steam turbines. Also, coal goes mostly through a steam turbine pathway for electrical conversion. There is solar PV, but I'm talking about the mirrors that uses sun's heat. I mentioned oil and gas being a big part of the energy infrastructure. Actually, every molecule of oil and gas that reaches its end use goes through at least 3 or 4, and maybe up to 10 different machines on its way through the processing and pipeline system. So a natural gas supply chain has gas processing plants, gas compressor stations, all with centrifugal compressors, reciprocating compressors, driven by gas turbines or natural gas engines. And then a lot of that gas goes to the electricity production, where a combined cycle gas turbine will have a really large gas turbine and large steam turbine for power generation. Oil pipelines are similar. There's a whole pump pipeline network. I've shown an electric motor as a driver here, but that could be an engine driver. And then they go to refineries, where they're converted for end use using whole arrays of pumps and compressors. Those are driven by gas turbines and steam turbines. And I'm not done yet, but I'll get there. On the end use, let's talk about residential applications. Most of us are aware there's a compressor in our air conditioning system. There's also fans, like inside a vacuum. There's a blower or a ceiling fan for moving air. As you go to commercial systems, we have larger HVAC systems, again, compressors and expanders sometimes. And just to pick on commercial medical use, there's even machines there. We spin magnets around people at really high speed in an MRI machine. There's a whole bunch of different industrial uses. So going from left to right, there's air blowers, there's processed gas compressors used in plastics production, there's heat pumps used in drying and cooling applications, or if we want to get really cold, like cryogenic expansion, we use liquid turbo expanders, shown in the bottom middle. Even pulp and paper uses large rollers, and food and beverage uses specialized pumps to move food products around. Transportation we're more familiar with, so reciprocating engines are ubiquitous in most automotive applications. They might be boosted with a turbocharger. Propulsion applications use jet engines as well as rocket turbopumps. Am I done? Almost. The world is looking towards decarbonization, and that also involves energy systems. So a lot of the energy ends up in that right bubble where it's rejected as low-grade waste heat. We're designing advanced power cycles that use machinery to convert that heat into electricity. These are like organic Rankine cycles or supercritical CO2 power cycles. Also, once we convert energy to electricity, if that comes from a variable source like solar or wind that's not available all the time, there's a large interest in energy storage to make that electricity available when we need it. And over 95% of the world's energy storage is still in machinery-based technologies like pumped hydro or compressed air energy storage. And finally, if we're going to keep using hydrocarbons to feed our energy demands, there's interest in carbon capture. And so you need CO2 compressors that feed into a whole CO2 pipeline station. So machinery is everywhere, I guess is the main point I want to make here. A couple other points. SwRI has been involved in projects that touch every single one of these kind of machines. So I've chosen all of those to represent that. And also the application areas here are very diverse. So there's a lot of collaboration between different research programs at SwRI as we investigate machinery in a system. That includes the chemical applications with chemical engineering, that includes a lot of collaboration with powertrain engineering and stationary systems and others. In addition to being ubiquitous throughout the economy, machinery systems are not new to SwRI. We've been dealing with machinery systems almost since our very beginning in the 1950s. The image on the upper right shows what's known as the analog for the gas compressor industry, and it's a machine that used resistors, capacitors, inductors to simulate with electrical dynamics the behavior of pulsations in gas pipelines, and allowed us to design engineering solutions in the piping system to mitigate those pulsations. We still do that work today, but we don't use analog computers anymore. Instead, we use digital simulations, and we also expanded our services into a whole different range of capabilities for analyzing, designing, and testing machinery in all the applications that I mentioned above. The pictures on the lower right really show the range of capabilities that we have in thermodynamics optimization, fluid and structural analysis, machine design, and then testing at small and large scales, as well as full power plant design. Every one of these pictures was taken and is tied to an internal research program that we've done to use the internal research program at SwRI to build our capabilities to branch into these new areas. We've also grown a lot as we've expanded. So that growth has been most pronounced in the last 15 years, where we started at about 38 people doing $8 million a year, to just last year we were 86 people doing $28 million of revenue. I mentioned testing was an important part of our growth. We got a real big shot in the arm in our testing capabilities back in 2012 when we built the Turbo Machinery Research Facility. That facility was built around a CO2 compressor that was powered at 3 megawatts, or about 4,000 horsepower, and we had a piping infrastructure as well as what you can't see as electrical and cooling capacities to feed that whole system. That was the initial system, but we used all that infrastructure to build out tests for other compressors, expanders, test rigs for bearings and seals, or other flow components and power systems. And the only limit we had was that we could only test with inert gases like CO2, nitrogen, and air. And that was primarily because of the indoor nature of the facility. But most of the applications I talked about actually use fluids that are flammable or have other energy content to them. And so as we started to develop the plans for a new facility, we kept 3 core capabilities in mind that the facility would handle. One is we wanted to test this machinery with its actual gases, with the actual behavior that makes the results most applicable to the end client. So we wanted to test gas compressors like shown here with their actual hydrocarbons. And that includes trending markets like liquefied natural gas as well as hydrocarbon-based propulsion. We had a small combustion facility on the side of the old facility, but we wanted to dramatically expand our capabilities. We wanted to get higher air supply, which we did with a large air compressor shown on the above. We wanted to enhance the range of fuels we could handle, which we did through a permitting amendment or modification, and expand the fuel rates we could do, which we did with a fuel compressor and fuel storage system shown in bottles. And what that did is expanded our capabilities. The chart shows the temperature of air we can provide to our combustion facility versus the flow rate we can provide. When we added all the fuel and air compression equipment, we almost tripled our flow capacity from 5 to almost 15 pounds per second. We almost tripled our pressure capacity, and we maintained the temperature to meet what we need to for our clients. And lastly, we also wanted to handle high-energy fluids that aren't just hydrocarbons that are used in industrial applications. So industrial applications might be things like heat pumps. The video in the middle shows a heat pump that we co-developed with a manufacturer and actually won SwRI's 54th R&D 100 award. And the other 2 pictures show a machine that would be used to displace a natural gas-fired propane cracker in a refinery by using steam and turbo machinery as energy addition. So we wanted to be able to test these in a new facility. So taking all those requirements together, we built a new facility. On the right shows our pre-existing turbo machinery research facility, and it had a porch extension where we upgraded the combustion facility as I described. The new construction is 3 new buildings. There's a large semi-open high bay where we do most of the powertrain testing inside there. We have a second building which houses a steam system. There's a process flare I'll talk more about in a moment. And then the left is where we control and energize all of the equipment from. On the far right is where we bring in fuels that's isolated from the rest of the equipment for protection and routing. If you're a molecule of fuel that we bring in, you get offloaded from a trailer in our fuel yard onto the pipe rack where you're metered and regulated. From there, you can go along the pipe rack and over to the new building if you take a left, or you can go straight to where our combustion facility is. The process flare on the right is used during venting and purging to ensure that we don't vent a flammable gas to atmosphere. Instead, we flare it. As we come around to this end, we get to where we have older infrastructure that we've tied in so we can bring CO2 and nitrogen as well as chilled water from our cooling tower over to feed both the old and the new facilities. All those different gases can go over to our combustion facility or they can take a left. And as we go left, we can approach the new building along the pipe rack where we can drop from anywhere along the edge and feed different arrangements of equipment. I mentioned that we had a need for steam, so we worked with the chemical engineering group and brought over a steam generator they were no longer using to feed steam across the pipe rack into the facility. In the facility, we can move equipment around with a 40-ton bridge crane. There are 4 different heavyweight machinery pads and a large electrical supply we can use to drive those, typically with motors, although we have enough gas to do it with a gas turbine. There's a pit for a lube oil system as well that we use to ensure that we can supply all the machinery needs. When we think about high energy fluids, we do of course think about safety, and this facility has been designed with the facilities team from the ground up with passive and active safety. So the facility's semi-open nature is a passive feature that allows for gases to ventilate and disperse if there are unintended leaks. All of the positioning of equipment out here was designed to be compliant with fire and electrical codes. The lube oil and supply and drain system is actually integrated through the foundation of the facility, which minimizes surface congestion and tripping hazards. The electronics are designed to be intrinsically safe or de-energized. And then finally, we have a network of monitoring systems with gas detectors, flame detectors, and then beacons and horns throughout the facility to provide notifications. Or we also have a system that shuts off the fuel supply if there's a safety issue that's observed. So, any questions?
We have one right back here.
Can you explain what high energy fluids are?
Okay, the question is, can you explain what high energy fluids are?
Yeah, we're primarily talking about hydrocarbons or other flammable gases. So it included natural gas, propane. We're not just talking about hydrocarbons, though. For industrial heat pumps, there are also flammable refrigerants that might be used. And because we have a remote site, we wanted the ability to consider testing certain gases that might be toxic, although each of those still requires its own separate safety analysis.
Any other questions for Tim? Right back here. How many different projects can you do all at one time?
That's a good question, and it doesn't have a specific answer because it depends on the energy needs of each project. What we find is that as we do these projects, there's a lot of time that's spent in the setup and the construction and then small energy input commissioning activities. And by the time it's all working, to run the actual high energy test only takes a few weeks. So we can build up multiple projects in the space at the same time, and then we have to just schedule the testing to juggle our energy inputs.
Did we have another one back here? Right there. Go ahead. Of the $28 million, how much was federal funds?
On $28 million, that's our revenue from 2025. About a third of that was federally funded. So 2/3 was commercially funded.
I think we're good on the questions. Thank you, Tim.